Hi, this is Barrett Givens, and in this video, I'm going to prove this theorem that characterizes the boundary of a set in a topological space. So far we know that the boundary of a set is the closure of the set minus the interior of the set. But this gives us another way to think about the points in the boundary. This says that a point is in the boundary if and only if every neighborhood of that point intersects both the set and its complement. Okay? So an element B is in the boundary of A if and only if every open neighborhood of B intersects both A and A complement. So I can sort of think about it with a Venn diagram. I can think about it if I have my set X like this, and I take a point or a set A. I want to sort of imagine B. I'm sort of imagining B on the boundary means B's right on the edge. So B is maybe right here. And then what it says is that every open set I take around B has some points that are inside of A and then some points that are outside of A. So it has to have some of like both kind of points inside A and points outside A. So every open neighborhood, which means an open set containing B, has to sort of look like this, where it has some points in A and some points in A complement. In a way, that's saying that B is both close to A and close to A complement. All right, let me just label that. That's A right there. Okay. And the statement is an if and only if statement. So to prove it, we have to do two directions. So we'll start the proof. All right. For the forward direction, suppose B is in the boundary of A. By definition, that means that B is in the closure of A minus the interior of A. That is the definition of boundary. What does it mean for a point to be in the difference of two sets? That means that B is in the closure of A and B is not in the interior of A. That's the meaning of set minus. Okay. Now we have a previous theorem about if B is in the closure of A, what does that mean? So since B is in the closure of A, every open neighborhood of B intersects A. That's a theorem we have about the closure. Okay, that a point is in the closure if every open neighborhood of it intersects A. So we're partway to proving what we want to prove. We want to prove that every open neighborhood of B intersects both A and A complement. Well, we got the A part now. Okay, so we know that every open neighborhood of B intersects A. Now, what about A complement? Well, B is not in the interior of A. To be in the interior would say that there is some open neighborhood that is contained in the interior. Okay, if B is not in the interior, like, let me say that again. If B were in the interior, that would mean that there exists an open set. So this is saying, so it is not true that there exists an open set U such that B is in U and U is a subset of A. Okay, so I'm saying that it's not in the interior, so this is not true. So there can't be an open set with this property. That means that every open set that contains B can't be a subset of A. What does it mean that you're not a subset of A? So that means U is not contained inside of A. So it means it must hit some of the points outside of A. So U intersects A complement. Okay. So we showed that every open neighborhood of B intersects A. And if A is an open neighborhood of B, sorry, if U is an open neighborhood of B, then U intersects A complement. So every open neighborhood of B intersects both A and A complement. And that was what we wanted to show. All right, so now let's go the other way. suppose it's really kind of the same thing. Every open neighborhood of B intersects both A and A complement. Well, because every open neighborhood of B intersects A, then B has to be in the closure of A. That's a theorem about the closure. Okay? And also, B is in the closure of A complement. That's a theorem about the closure of A complement. But we also have a theorem that says the closure of A complement is the interior of A complement. The closure of A complement is the complement of the interior of A. Thus, B is in the interior of A complement. But the meaning of being in a set complement means you're not in the set. So B is not in the interior of A. So B is in the closure of A, but it's not in the interior of A. Thus, B is in the closure of A minus the interior of A. And of course, that's the definition of the boundary. Okay. So this theorem is just going to be very useful when you're trying to look at a particular set and you're looking at individual points and you're saying, well, is this point in the boundary or is this point in the boundary? Or maybe you're looking at different types of points. You're saying like, well, would points over in this region be in the boundary? Would points in this region be in the boundary? This is the test that you use to determine if certain points are in the boundary of a set or not. Okay. Thank you for listening.